Okay, good morning, everyone. So, I hear you guys have a midterm tomorrow. So hopefully you're ready. So, we said this before, but how do you prepare for the midterm? Basically, make sure you go over the lectures, slides, and make sure you understand everything. Make sure you go over the homework solutions, the recitations, and the solutions of the recitations. And then you should be in good shape. Okay, so today we're gonna, this is gonna be part 3 of Introduction to Computational Complexity. And today we're gonna talk about space complexity and circuit complexity. And actually, in fact, also how these things relate to time complexity. Okay, what we've discussed in the previous 2 lectures. Okay, so let's start with space complexity. So how should we define space complexity of an algorithm? Okay. So there's an obvious answer to this. You can say, well, just look at, if you're talking about the Turing machine, just let's look at the number of tape cells that the Turing machine accesses. Okay, and you could define it that way. But here's a question. Should the input count? So suppose like you have an algorithm and it's, let's say, reading some information from a gigantic file. Okay, it has gigabytes of information. Or you have an algorithm that's going through the internet and looking, taking information from the internet and doing something with that. And the internet is pretty big. So should we like consider the size of the internet as contributing to the space complexity of the algorithm? Okay, so I think, well, the convention we use is that we shouldn't really consider the input of the algorithm as counting towards the space complexity of the algorithm. Okay, so a Turing machine then we can say has space complexity S if for every input X it uses only S, the size of X cells of the tape. This is sort of the first kind of definition I gave you. But, you know, for a one-tape Turing machine, right, if the size of the S of n has to be at least n if we are going to read the input, right? And this is really not the way we actually define space complexity. So to define space complexity, we could define it using a one-tape Turing machine, I guess, but it's not very neat. So the neatest way to define space complexity is using a 2-tape Turing machine. Okay, so we're going to have 2 tapes. We're going to consider 2-tape Turing machine. The first tape is going to be reserved for the input. So the input is going to be written on the input tape. And this is a read-only tape in the sense that you're not, or the Turing machine is not allowed to write on the read-only input tape. Okay, it's only allowed to read from it. And then there's a second tape, tape 2. It's called the work tape. And this is where basically your Turing machine can do its computations. And this is, of course, readable and writable. Okay. And then the space complexity of such a machine is going to be just the number of work tape cells that the machine is using. Okay? So let's look at some examples. Our favorite language here, 0 to the k, 1 to the k. And we've seen an algorithm for this already. Scan the input and reject if there is any zeros found to the right of a 1. Okay, and then again, you scan the tape, you scan the input, and for every 0, you cross a 0, and then you go cross off a corresponding 1, cross off a 0, cross off a corresponding 1, and so on. The thing is, this was for one tape Turing machine. And when we are measuring space complexity, this is not the model we use, but you could easily adapt this to the two-tape machine. But if you want to do this, what you will have to do is copy first the input to your work tape, and then do the crossing off. Okay? And that will take order and space, right? Okay. Here is another algorithm for the same language, but now this is going to be more space efficient. So you scan the input again, the first step is the same, and then you basically count the number of zeros and then count the number of ones, and then you compare them, right? So the first step makes sure that they're in the right order, and then in the second step you basically count the number of zeros and ones. So what's the space complexity going to be for this one? It's going to be big O of log n space. Why? Because basically this real space you're using is for counting, right? And k, the input length is n. K is going to be like n over 2 if, well, you're going to count basically up to at most n, right? Because the input is of length n. And if you want to count up to n, you can use that using log n bits. Okay. Now let's look at another way of expressing an algorithm, a Python function. This is the two-finger algorithm. Okay, so you have two fingers. The first one is at the start, the second one is at the end, and you're checking is this a 0 and a 1. 0 and a 1, 0 and a 1, 0 and a 1, 0 and a 1. So we've seen this before as well. So what's the space complexity of this one? What's it? Constant. Anyone else? So first of all, it's good because you look at this, S is the input, right? And we're not modifying S. So in that sense, it's good that we're not modifying S. Yes, so it's again big O of log n, because if you look at this, what we're doing is we have two basically variables, low and high, and the values they take is between 0 and n. And to represent that value, all we need is log n bits. Okay, and in the other parts of the function, we're not really using extra space. We're just reading from the input and then doing some basic arithmetic. Okay, so this is again order log n space. Okay, so if you think about you can ask, what can a log space machine do? A machine that is bounded by order log n space. Well, here are a few things that it can do. It can keep a pointer to a constant number of positions in the input. Just like in the previous algorithm that we saw, we had like 2 pointers to the input. And a pointer to the input is just going to be log n bits long, because the input is going to be n bits. You can count up to some polynomial in n to the k. Okay, why can you do that? Because if you're counting up to poly n, let's say n to the k, to represent that you need log base 2 n to the k bits. And that's going to be by the properties of the logarithmic function k times log base 2 of n. Okay, so it's big O of log n. And you can also keep logarithmic number of Boolean variables. Boolean variables store just 0 or 1. There are constant amount of information there. So you can keep a logarithmic number of these Boolean variables or flags, or whatever you want to call them. Okay, you might say, well, you know, a log space machine can read, all it can do is like these kind of things. Let's look at an interesting problem. This is called the reachability problem. Okay, so the input in this problem is a set of cities and a set of roads between these cities. And you're also given two specific cities in this collection, S and T. And the algorithm is supposed to output yes if we can reach T from S. Okay, if there's a path from S to T and no otherwise. So we can represent an input of this form like this. So each node here, each vertex corresponds to a city, and we put a road between two cities if there's a road between them. And we're given two vertices S and T, and we're asked, is there a path basically from S to T in this structure? By the way, this kind of a thing is called a graph in computer science and math. It has 5 nodes or vertices and 6 edges. And in fact, these things are so important that the next 3 lectures is going to be devoted to studying just these kinds of objects. Okay, because it turns out like a vast number of computational problems, an incredible number of computational problems can be represented as a graph. So it's very important to study such objects, and we're going to do that. But anyway, so you're given this problem. Now, imagine like your graph has millions of vertices, okay, and you are given some connections between these vertices nodes, and you're given like 2 points in this graph, S and T, and you're asked, is there a path from S and T? Okay. So what can you do? Well, you can say, okay, I'll start from S, and then I'll just like explore the neighborhood of S, go to its neighbors, and then I'll explore the neighbors of that, and so on, and at some point try to reach T in some way, right? But like you're a log space, let's say you want to do this in log space. You're a log space bounded machine. In some sense, you're like a nearsighted or almost blind guy, right? So you cannot see far ahead. Okay, so you can only remember, you can only see what's near you, and you can only remember what's near you in some sense. Okay, and you're at S, and you're trying to find T in this, millions of vertices. Right? It seems like it's impossible to do. Okay, you can only keep track of, you can only remember a constant number of vertices in this graph, because when one vertex is log n bits of information. Okay, you can only remember a constant number of these vertices at a time. So how are you going to make sure that you will be able to reach T if you can, or you won't reach T if you can't? So this seems like, it's impossible to do in log n space, but one of the most celebrated results in computational complexity theory says that this can be done in ordered log n space. Okay, this is by Amar Reingold from 2004. But unfortunately, it's beyond the scope of this course, but I hope like if you take an advanced computational complexity course that you see this algorithm, because it's quite fantastic. All right, here's another example. So we saw satisfiability problem. We saw it before. Given a Boolean formula, is it satisfiable or not? Just something like this. We can rephrase this question and say, here, does there exist an assignment to x1, an assignment to x2, an assignment to xn, such that this Boolean formula, which I'm going to represent it as phi of x1 to xn, is satisfiable? Okay, so is this like sentence basically true or not? Our domain is 0, 1, right? Each variable can get the value 0 or 1. Now there is and this is a very important problem, we're going to come back to this, but there's a very related problem, a generalization of this called QSAT, quantified SAT, or TQBF, which stands for True Quantified Boolean Formulas. And this is like, given a quantified Boolean formula, is it true? But now, in SAT, all the quantifiers where there exists, now they can be there exists or for all. Okay? And also, we're going to make a slight modification. We're going to allow phi to have constants, 0 and 1. Okay, so I could have a formula which says x1 or 1, let's say. Okay, and this is also a very important problem in computational complexity theory, it turns out. So this problem actually cannot be decided in logarithmic space, but it can be decided in polynomial space. And in some sense, it captures the essence of algorithms that use polynomial amount of space. But I'm not going to really explain why that's true, but it is the case. So I'm going to now actually sketch to you why this is in polynomial space. And we're going to also see an interesting feature of space, which is different from time. And the feature is that, well, space, unlike time, is reusable. Okay? And that seems to give it more power. Time, unfortunately, unless you're time traveling to the past, cannot be reused. Okay, so let's sketch the argument that this is in polynomial space. So the size of phi, let's say it's m. Okay, we have n quantifiers. So really the size of the input here is big O of n plus m. So you see sometimes we don't actually use n for the input length, right? Sometimes n is convenient to use for some other parameter, but then we're going to be clear about what the input length is, so there's not going to be any ambiguity. Okay, so the size of the input is m plus m. And then let's make a definition here. So given some quantified Boolean formula psi, let's denote by psi with the restriction that x1 equals b. And here b is either 0 or 1. This is going to be the same as psi, but we're going to drop the q1, the first quantifier. Okay, and all the occurrences of x1 in the formula phi is going to be replaced with b. Okay, and b, as I said, is 0 or 1. Okay, so that's just a notation. Now here is the algorithm that's going to decide this problem. A is the algorithm, takes a psi quantified Boolean formula as input. The first thing is we're going to do is we're going to check, is n equals to 0? If n equals 0, there's no quantifiers, right? And your formula phi is just consists of constants, right? So in this case, you just do it. Okay, I'm not going to tell you actually how to do it, but you just compute it, and then that takes about big O of m space. Now, what's the next step? So we're going to check if the quantifier, the first quantifier, there exists. Okay, if the first quantifier exists, then we're going to run our algorithm recursively on the restriction when x1 is 0 and also on the restriction when x1 equals 1. Right? So we're going to get rid of the first quantifier, and we're going to replace x1 with 0 first, and now also we're going to replace x1 with 1. Now if one of these returns true, it says it's satisfiable, then it's satisfiable, right? Because my quantifier was there exists. It's saying, does there exist a value for x1, 0 or 1, that makes this true? And then if the quantifier is for all, what am I going to do? Same thing with and, right? Output A restriction x1 0 and x1 restriction 1. So it kind of seems like I'm making 4 recursive calls, but not really, right? I'm computing this value and this value, 2 recursive calls, and then I'm either going to take the or of those or the and of those. Okay? So then let's denote by S n comma m to be the space used by algorithm A. Now here's the important observation. Okay? So these recursive calls that we're making 2 of them. they can use the same space. So you can compute the first one, the first recursive call. It uses some space. You get an answer, 0 or 1, true or false. You store that answer, 1 bit of information, and then all that space you use to compute the first recursive call, you can reuse that to do the second recursive call. Okay, so that's the advantage of space that we're using. And then if you do that, you can write a recursive relation for S n comma m. And that's going to be basically S of n minus 1 comma m. That's for the space that you're using for the recursive call. Plus, you can say, well, it's at most like n plus m because, well, I'll need to maybe write this input down for A. And if I write that input down, well, that's like order n plus m bits. But this is like a rough upper bound. If you can be a bit more careful about your analysis here and get a better bound. But this basically gives you, and this is an easy recursion to solve, it's n times m plus n squared, which is basically at most quadratic in the input length. Okay? And as I said, actually, you can do the analysis a bit more carefully, and you can get actually linear space. Not quadratic, but linear. Yeah?
How would you define space complexity for, like, languages like we use now? Like, is it the most memory used at any given time?
It's the number of well, if you can like map your algorithm into like a 2-tape Turing machine structure, it's like the number of work tape cells that you're using, right? At any given time unit, you can only access one memory cell, right. One unit, okay? Okay, good. All right, so that was an interesting example. Now, recall the time complexity classes that we defined in the last lecture, because I'm going to do the same for space complexity and define space complexity classes. So these were the time complexity classes we had. We defined d time t of n to be all those languages that can be decided in big O of t of n time. And then we defined polynomial time, languages that can be decided in polynomial time, basically. Exponential time and exponential class. So these are all the languages in P. Those are all the languages in exp. Of course, P is a subset of exp. But you could ask, of course, is P equal to exp? Are these two sets actually equal or not? And then we saw very quickly, I stated this time hierarchy theorem that showed that actually these two sets are not equal. Okay. Now for space complexity, we can do d space S of n. This is the set of all languages decided by big O of S of n space algorithm. We can define polynomial space, right? So languages that require that can be solved using polynomial amount of space. We can define log space, which is denoted by L, another very important complexity class, which is d space log of n. Okay, so this is big O of log of n. And by definition, of course, you can see that L is contained in P space. Okay, so we have a picture like this. But again, you can ask, well, is L equal to P space or not? Okay, so that's an interesting, important question. And similar to the fact that we had that P is different from X, we can also show that L is different from P space. And again, this is done through the hierarchy theorem for space. So the hierarchy theorems, just to recall, so this was the time hierarchy theorem. So the first sentence says, let Tm be a time constructible function. I didn't really tell you what this means. And I'm not going to tell you what that means. It's not very important, okay? So it's just some technical condition that you need. But the point is that it says that there is always a problem which cannot be decided in time t of n, but can be decided in, let's say, t of n to the power 1 plus epsilon. Okay? And from this, trivially it follows that P cannot be the same as exp. The complexity class P cannot be the same as exp. And we have a very similar space hierarchy theorem. This time, the technical condition is that S of n is supposed to be space constructible. Again, don't worry about that. But it says that there is a problem which cannot be decided in space S of n, but can be decided in space S of n to the power 1 plus epsilon. Okay? So another way of saying is this. And yeah, so this basically as a corollary, we get that L is not the same as P space. It's a subset, but there's this crucial mark there that says it's not equal. It's a proper subset. So, in fact, there are some languages living in this area, which is not in L, but in P space. Okay, so now we have these two. Well, we have 4 complexity classes now, actually. 2 time complexity classes, P and exp, and 2 space complexity classes, L and P space. Okay, and complexity theorists like to study the relationships between these 2 classes and understand them better. So to understand like the relationship between space and time as a resource, you want to first maybe try to understand how do these different complexity classes relate to one another? Okay, so when these things try to come together, what happens? Okay, what's the picture really? What does the picture look like? Okay, so we're gonna determine now. We're gonna figure out, try to figure out how this picture looks like. Okay. So we're going to look at the relationship between space and time, and the crucial theorem here is going to be the following. So if we have a Turing machine that decides a language using, S space, and we're going to assume here that S of n is at least log of n, then it is decided in time 2 to the big O of S of n. Okay. So suppose you had, for example, a log space machine. It uses log n space, order log n space. This theorem is telling you that, well, it can be decided in time 2 to the big O of log of n, 2 to the c times log of n, which is going to be n to the c, actually. It's a polynomial time. So a log space algorithm can always be decided in polynomial time. And I'm going to state this again later. But this is the basic fact, so let's prove this first. Okay, so here's the proof. So the proof is going to use the concept of a configuration. Okay, so we've seen this before. A configuration of a Turing machine is just a string like this, U, Q, V, where U and V are some strings, and Q is some state. Okay, and this is a configuration is like a snapshot of the computation. Okay, and then you say, okay, what does a configuration really, what kind of information does the configuration encode? So there are 3 things that it encodes. First of all, it encodes the current state that the machine is in. It encodes the position of the tape head, right? Where is the head of the machine? And then it also encodes the contents of the tape, right? So 3 information. Now, we are working in the setting of space complexity. We're interested in space complexity, so we are really thinking about now 2 tape Turing machines, right? A read-only input tape and a read-write work tape. So really now a configuration for us is going to encode the current state, yes, the position of the tape head, but now there are 2 heads, one for the input, that should be work should be work and input tape. So one for the work tape, one for the input tape, and then also contents of the work tape. Because as we said, the input tape is read-only, so that the contents there does not change. Okay, so this is the information that's encoded in a configuration. Now let's make some observations. Okay, so we already know that if the Turing machine takes t steps when given some input, then there's a sequence of configurations it goes through, right? C1, C2, up to CT. Now the first observation, which I hope you already know because you've done question 5C of the last homework, right? The first observation is that Ci cannot equal to Cj for I different from j. Okay, so you cannot have a repeated configuration in the sequence, because if you have a repeat, that means you're going to have an infinite loop, right? If like C7 is the same as C20, right? Then so C20 is C7 as well. So then you're going to go between those two configurations all the time. You're just going to get stuck. And then the second, so the Turing machine would be an infinite loop. And the second observation is that given that we need like all these CIs are distinct configurations, T here, the number of configurations you see, has to be upper bounded by the number of possible configurations you can have. Right? You cannot have T to be more than the number of possible configurations because there's no repetition among these configurations. They're all distinct. Okay. So the number of possible configurations then, what is that? Because if we can show that T, which is the time that the Turing machine takes, if T is at most 2 to the big O of S of n, we're done. Right? That's what we're trying to do. Okay, so if we show that the number of possible configurations is big O, is at most 2 to the big O of S of n, we're done. Okay, well, let's look at the number of possible configurations. So here is an expression. Here is the number of possible configurations that we have. So where does these quantities come from? So where does Q come from? Anyone? Number of states, right? So, and configuration has to encode the current state. And we have Q many states. Where does N come from? The input, yes. But more specifically, exactly. So where is the input head? In which location is the input head? That's N. Then S of N, where does that come from? Where is the head in the work tape? It can be in at most S of N locations. And then the last one. What's that?
In each of the locations you can be in, it can be one of any letter in the alphabet.
Right, so contents of the work tape. Right, so that's the last one is for the contents of the work tape. Okay? So then you say, okay, so this is the number of possible configurations I can have. Q, the size of Q is just some constant. Okay, it does not depend on N, so I'm going to write C for that. And then everything else, I'm going to write it as 2 to the something in that format. Okay, so if you write N at that format, it's 2 to the log base 2 of N. The S of N is 2 to the log base 2 S of N. And then I can write gamma, the size of gamma, as 2 to the log base 2 of gamma. So this gamma to the S of N can be written as this. Okay, so the next step is pretty clear. Put the exponents together, add them up. Okay, and now you see, okay, I have log N, log of S of N, and big O of S of N. Yes?
Can you use this to determine a time threshold such that if we exceed it, then we know for sure that the program is not going to halt?
Yes. Well, yes, exactly. Well, just like 5C of the homework. If you remember 5C from the last homework. Okay, so yes, but you're right. I mean, you can exactly do that. You can say, well, if it's running for more than a certain number of, more than the number of possible configurations, well, then it must be in a loop. Okay, so anyway, so we assume that S of n is at least log of n, by the way, right? That was one of the assumptions in the theorem. So because of that, since S of n is at least log of n, so all of this is really going to be big O of S of n. Okay? So log of n is big O of S of n, log base 2 S of n is big O of S of n, and this is big O of S of n. You add them up, it's big O of S of n. And that's it, right? So we show that t is at most 2 to the big O of S of n, and that's exactly what we wanted. Yeah.
But then we are working with a multi-tape theorem machine, and then we are talking about the number of steps, the number of possible configurations on a multi-tape theorem machine.
Yes.
So when we are going for the actual time complexity, don't we usually mean that we're talking about a single-tape theorem machine?
So in that case, we're talking about a two-tape, time complex of a two-tape Turing machine.
So are we allowed to actually switch models in this case?
Yes, because they are. You can work with a two-tape machine because I think like every one-tape machine, every two-tape machine can be simulated by a one-tape machine with a quadratic slowdown, I think.
Yeah, that doesn't
Yeah.
change the time complexity.
By a polynomial factor, but what's a polynomial factor between friends? Yeah, so quadratic factors, we're not, polynomial factors, we're not too, in this setting, we're not too worried about. Okay, but yeah, I mean, our setting here in this case is a two-tape machine, yeah. Okay, so this is basically what we showed to the big O of S of n. So as a corollary, as I mentioned actually, this shows that L, the complexity class log space, is contained in complexity class P. Right? Because if you have a order log n space machine, let's say it uses C times log n space, then 2 to the C times log n is going to be just n to the c time. And similarly, we can say that P space, polynomial space, is contained in exponential time. So this is our picture. Okay? So nested structure, L is contained in P. Now P is contained in P space. Why? Why is P contained in P space? Right, so in each time unit, you can access at most one new cell. Right, so if you're running in polynomial time, you can use at most polynomial space. Right, because at each time unit, you access at most one new cell. Right, so that's that. So here, then what do we know about this chain of inclusions? Well, one thing we do know about this chain of inclusions is that by the space hierarchy theorem, L is not equal to P space. And since L is not equal to P space, one of two things has to be true. Either L is not going to be equal to P, or P is not going to be equal to P space. Okay? Because if they're both equal, then L would be equal to P space, but we know that's not true. Now we talk about, P versus NP question as the $1 million question in complexity theory, but effectively these questions, whether L is equal to P or whether P is equal to P space, they're also like, well, they don't have $1 million price tag, but essentially, you can think of it as the same kind of, same order magnitude problem. They are, as like the importance of the problem, I would say they're like theta of each other, okay, in some sense. There's some constant differences, constant factors, but like they're very, all very important problems. And similarly, we know that P is different from, is not equal to X, which means that either P is not equal to P space or P space is not equal to X. Now, P versus P space question is in some sense a very interesting question because in a sense it's asking how do the time resource and the space resource compare with respect to efficient computation? Right? Is time and space pretty much equivalent? If P is equal to P space, in some sense you're saying time and space, you know, up to polynomial factors is pretty much equivalent, okay, as a resource. P not equal to P space means that time and space are actually not equivalent. They're different, okay? And you would think, your intuition would tell you that they shouldn't be equivalent up to polynomial factors because, well, as we said, space, you can reuse space. Time, you cannot reuse time, right? So they seem to be fundamentally different. Okay, but we cannot translate that intuition into a proof and say that, you know what, P is different from P space. Okay. So if you wanted to show P equals P space, what would you need to do, basically? Well, you would need a language A, which is in P space, but not in polynomial time, doable in polynomial time. Okay, so this part is easy, usually, to show. Take a language, it's P space. This one is the real hard question, showing that a language cannot be done in polynomial time. Okay, that's very hard because, as we saw, like from last lecture, polynomial time algorithms can really do tricky things. So you have to argue against all possible polynomial time algorithms and say, no matter what polytime algorithm you choose, it cannot compute or it cannot decide the language A. So we don't know how to attack that. Okay. So that's basically space complexity, all I wanted to say about space complexity. Now we move on to a sort of a different computational model, circuit complexity, which is a very interesting model of computation. It's different from the Turing machine model in some fundamental ways, and we're going to discuss that. But it's also related to the Turing machine model and the time complexity. And you know, people have studied this model a lot. It's an important model. So let me say a few words about that. And you know what? We defined circuits in lecture 2, right? So this was a circuit. In homework 1, you worked with circuits. You proved upper bounds. You proved lower bounds, right? So we are familiar with circuits already. So it looks something like this, right? So you have some inputs, input variables. You have some gates, AND gates, OR gates, NOT gates. You have wires connecting them. And then you have some output gate that gives you the output of the circuit. And this kind of circuit naturally computes a function, right, from n variables and outputs 0 or 1. Okay, so a circuit basically is a collection of gates and inputs connected by wires. We're going to consider circuits that have just 3 types of gates: binary AND gate, binary OR gate, and unary NOT gate. Binary AND means like it takes 2 inputs. Binary OR takes 2 inputs. Unary NOT takes 1 input. So as we said, like this naturally computes a function f(0,1) to the n to 0, 1. Or you can say it decides a language, L sub n, which is a subset of 0, 1 to the n. Now, I hope at this point you see a crucial difference between the Turing machine model. So what's the difference here? Yes.
Instead of accept reject, the output is 0, 1.
Yes, but that's okay. I mean, you can. That's okay.
The input is a fixed size.
Yes, the input is a fixed size, n bits, right? A circuit by itself cannot handle all input lengths. I have a circuit, it takes a certain number of inputs, and that's it. You know, that circuit is not going to handle larger inputs. Okay, if I want to handle larger size inputs, I need to construct another circuit. Okay, so really I need a circuit for each input length when I'm talking about circuits. So that's why when we talk about circuits, we're really talking about a circuit family. Okay, so a circuit family is denoted by C, is a collection of circuits, C0, C1, C2, dot, 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 where each Cn takes n inputs, input variables, and handles the case for inputs of size n. And then you can say, okay, let L sub n be the language decided by C sub n. And then we can say, well, the language decided by the circuit family is going to be just the union of all these L sub n's. Nice, okay? So what is the crucial difference now? If we define circuits in this way, what's the crucial difference between circuits and Turing machines? So if you recall this quote by Stephen Kleene, who said, an algorithm is a finite answer to an infinite number of questions. Okay, so why did he say that? Because if you have a Turing machine that computes a function, let's say f from 0, 1 to the star to 0, 1, this is the computational problem. It's an infinite number of questions. For each string, you're asking, is it in the language or not? And your Turing machine is able to answer all those infinitely many questions, whatever you ask. But the Turing machine itself, if you look at it, is just a constant size machine. The length, the size of the Turing machine does not depend on the input size. Right? So think about like if you write a function in Python, is prime function, let's say. It has, I don't know, 5 lines of code or something, right? It's a finite, some constant number of length description. It answers infinitely many questions, though. For each number, it tells you whether it's prime or not. Now, you can ask, what would be the corresponding quote for circuits? And I don't think anyone said it, so I'll say it. A circuit family is an infinite answer to an infinite number of questions. Okay, so this is not as profound as the other one, but you know, it's true. Okay, because for each input length, you need a circuit. Okay, so you need a circuit for each input length means you need infinitely many circuits to handle all possible input lengths. So then you might say, you know, this is perhaps not a very realistic model of computation. And in some sense, yes, you know, it's not very realistic maybe, but you might be interested in a fixed size input. You might say, well, maybe, you know, integers are 64 bits long, so maybe I'm only interested in circuits that take 64 bits. You might be interested in that, and just arguing about that case can give you insights. It is what we call a non-uniform model. It's not important. The technical definition is not very important, but you might hear it. So it's non-uniform in the sense that basically you need a different circuit for each input length, and these circuits don't have to necessarily be related to each other, actually. They don't have to look the same, for example, or similar. Now, if you remember from lecture 2, every function is computable in this model. Right? So every function, as we saw, has a formula, Boolean formula that describes it, that computes it. And every Boolean formula can be represented by a circuit. Right? So every function is computable in this model. So you might say, you know, it doesn't seem realistic. Everything is computable, so maybe this is not a very useful thing to study. But actually, it is a very useful model to study. So maybe I'll try to convince you of this in the remaining 15 minutes. So first, let's define what we mean by a circuit size. What's the complexity measure associated with circuits? It's the circuit size, which is basically the number of gates in the circuit. Now I'm going to count the input variables as gates too. You don't have to. It's not a crucial difference, but you can, and I will. And then you can say the size of a circuit is just a function, small s, such that S of n is the size of C sub n. Right, so exactly what you would expect. And then the circuit complexity of a language is the minimal circuit family that decides the language. In some sense, it's the intrinsic complexity with respect to circuit size. Now, in this particular case, actually, this circuit complexity is well defined, unlike intrinsic complexity. Because we saw in intrinsic complexity, you could potentially have, you don't necessarily have to have an algorithm that has the best running time. So you could have a family of algorithms that gets like better and better and better and better in terms of big O. But in this case, that's not a problem. So circuit complexity, this is well defined because you can say, okay, given a language, I can say, okay, go through, I'm going to look at inputs of length 1, go through every circuit that takes one input, and take the one of minimal size that computes the language for that input, and then go to inputs of length 2, go through each circuit of that takes 2 inputs, take the minimum one that computes the function, and we'll take that one, and so on. So for each input length, I can take the minimum size circuit, and that will be well defined. Okay, and then the size of S of n. So we say a language is in the size of S of n if there's a circuit family of size big O of S of n that decides that. Okay, so we know every function is computable by some circuit family. But we can ask, what is the maximum size of a circuit that computes a certain function? Okay, and here's the theorem. For every language A is in size 2 to the n. So using exponentially many gates, you can compute any function, decide any language. Okay, so let me quickly go over the proof of this. So let's say that f sub a 0,1 to the n to 0,1 corresponds to the language A. So we're going to have such function for each n, of course. And we'll assume, you know what? We'll assume implicitly that A is the language that requires the most number of gates. The language that has the largest circuit complexity. So here's an observation. So you can say that f of fa x1 to xn, you can write it as, well, x1 and f of a with x1 fixed to 1, or the knot of x1 and f of a with x1 fixed to 0. I mean, I'm not going to formally prove this, but this is quite easy to see why this is true. Okay, and then that suggests the following picture when you want to compute f of a. you recursively compute it, right? So you have a circuit where that computes f of a when the first input is fixed to 1. You have another circuit that computes f sub a where the first input is fixed to 0. Here's my inputs. x2 to xn are feeding into this subcircuit and the right subcircuit, right? And then what do? I take x1, I AND it with the output of this one. I then negate it and AND it with the output of that one. So exactly, basically this, you take this, you draw the picture, it's this, right? And then you can say, okay, what kind of recursive relation do I get for the size? Well, the size is going to be at most, an upper bound, 2 times s of n minus 1 plus 5 more gates. 1, 2, 3, 4. 1 for the x1, 5. So that's an upper bound for sure. You can check that for length of input 1, it's at most 3. And then that says, okay, S of n is, you solve it, it's easy to solve, it's big O of 2 to the n. So, okay. So that tells us that we can compute every function in exponential size. Then we can ask, well, is there any function that actually requires exponential size circuits? Or maybe every function is computed by polynomial size circuits. Is that possible? And that's actually not possible. So here's a theorem. There's a language L whose circuit complexity is at least 2 to the n over 4n. Okay, so that's not really omega 2 to the n, but it's quite close. Okay, so there are some languages which require exponential size circuits. So how does the proof of that go? So it's quite neat, actually. Let me show you. So we want to show that there is a function f01 to the n to 01 that cannot be computed by a circuit of size less than 2 to the n over 4n. Okay? So if we take this function, if such a function exists, then we'll take the union of these functions for all n, and that's the language we are looking for. All right. There we go. So number of possible functions. Kind of gave away the answer, but what's the number of possible functions that we can have? So we're going to do a counting argument here. We're going to count the number of possible functions, and we're going to count the number of possible circuits of a certain size and see that things are not going to match up. So what's the number of possible functions that I can have? It's 2 to the 2 to the n. I think we've discussed this in lecture 2 or something. Now I'm going to make 2 claims. And the result is going to basically follow from these 2 claims. The first claim is that the number of circuits of certain size s is at most 2 to the 4s log s. Okay, I'm gonna prove this claim. The second claim is that if s is less than or equal to 2 to the n over 4n, then 2 to the 4s log s is less than 2 to the 2 to the n. Okay, so what does this say? If the size s is less than 2 to the n over 4n, then the number of possible circuits of that size is strictly less than the number of possible Boolean functions. But each circuit computes 1 Boolean function. So there must be some function that cannot be computed using at most that size. Okay. Okay, so basically the result follows from these 2 claims. So let's take these 2 claims. The second one, I mean, it has nothing to do with circuits or anything conceptually. It's just numbers. You can verify it yourself. Okay, so it's just manipulating these numbers, and you see that it's true. So the real thing is claim 1 here, proving claim 1. So here's what we're going to do. To prove claim 1, that number of circuits of size s is less than or equal to 2 to the 4s log s. For each circuit of size s, we're going to create a binary string of length at most 4s log s. Okay, so I'm effectively defining a map that's a mapping from the set of circuits of size s to binary strings of this length. Okay, it's a mapping. And this mapping will be injective. Okay, so if this mapping is injective, then what do we know? Then we know that the size of the possible number of circuits of size s is going to be less than or equal to the number of possible binary strings of this length, which is 2 to the power of that, right? 2 to the power 4s log s. And that's exactly what we're trying to prove in claim 1. Okay? So let's do that then. Let's show a mapping from the circuits to binary strings of length n. And to do that, what we're going to do is we're going to take a circuit and we're going to show how we can encode it using a string of this length. So let's number the gates 1, 2, 3, 4 up to s. For each gate in the circuit, we're going to write down first the type of the gate. And then the second thing we're going to write down is from which gates the inputs are coming from to that gate. Okay? And if you write this information down for each gate, then that basically describes you the circuit. Okay? From this description, I can construct you the circuit. Okay? So, how many bits do I need for the type of the gate? 2 bits. I have 3 gates. 2 bits is enough. From which gates the inputs are coming from? So for a fixed gate, how many bits do I need? 2 log s. Very good. So I have 2 inputs. Each gate is represented with log s bits. So that's 2 log s bits. And then I do this for each gate. So there are s many of them. So I have s times 2 bits plus 2 log s bits. So this is basically 2s plus 2s log s. But s log s is like larger than s. So I can upper bound this by 4s log s. And I'm done. Okay, so that's a very nice counting argument. And that was basically done by this guy, Claude Shannon, in 1949. He's considered to be the father of information theory. And we might actually talk about information theory towards the end of the course. Now, this is what we call a non-constructive argument. It's non-constructive in the sense that it says there is some function that requires exponential size circuits, but it gives us no idea about what that function might look like. Okay, we have no idea what this function is, what it looks like. So in that sense, it's non-constructive. And in fact, you can sort of tweak this argument just a little bit and say and show that a vast majority of the functions actually require exponential size circuits. Not just one, but a vast majority of them. Almost all of them require exponential size circuits. Okay, so let's keep that information in our pocket. Okay, so almost all functions require exponential size circuits. Okay, and let me now tell you the connection between circuit complexity and time complexity. I'm not going to prove this, but it's a very important connection. It says that if you have a language that can be decided in time t of n, then it can be computed by a circuit of size t of n squared. For example, if T of n was polynomial, so if A was in P, polynomial time, then you can say that it actually also has polynomial size circuits computing it. So you could say as a corollary, if A cannot be computed by polynomial size circuits, then A cannot be in P. So it gives us a way to prove that some language is not in P. So for example, to show that P is not equal to P space, find a language in P space that cannot be computed by polynomial size circuits. Okay, seems promising. So what's the current state of affairs in this? So you guys actually showed a circuit lower bound, right, in homework 1. You showed that there was a function that required, I think, 2n minus 3 gates. But those circuits were sort of actually more general. You were allowed to have any kind of binary gates. Here we're only looking at AND or NOT gates. So what do you think is the best lower bound we know for any kind of explicit function? It doesn't even have to be in P space, but it could be. What do you think the best lower bound we have currently for any explicit function, any kind of explicit function? One guess. Who'd like to guess? N? Well, you showed 2n minus 3 in the homework. So it has to be 2 to the n, exponential size. So okay, you don't want to volunteer. After 60 years of research, best lower bound for an explicit function is, drum roll, 5n minus peanuts. So peanuts means basically something smaller, very small, it doesn't matter. So essentially you can think of this lower bound as 5n. Okay, so the best lower bound we can show is 5n. And you guys came close. You guys did 2n minus 3. So advantages of working with circuits is basically, you know, a Turing machine model is nice, but it sort of doesn't have a very clean mathematical definition. But a circuit has a very clean and simple mathematical definition. And so it seems reasonable to, you know, work with circuits and try to prove circuit lower bounds. It's, you know, seems better to approach it that way than to work with Turing machine models. And it's easy to create a hierarchy of problems too. You can restrict your circuit. So, okay, I cannot prove a lower bound for polynomial size circuits. It's too powerful. Let me restrict the circuit. Let me say, for example, restrict the depth of the circuit. The depth of the circuit is basically the longest, the length of the longest path from an input to the output node. Okay, I can look at constant depth, log n depth, and, you know, restrict the size of, restrict the circuit, and maybe I can prove lower bounds then, and maybe that will give me insights about how to prove lower bounds for the general case, and so on and so forth. And basically, this is what people did in the 80s. In the 80s, like, people had really nice results along these lines, and people were very confident that, you know what, all the questions that we want to answer about complexity, P versus MP, P versus P space, we're going to solve these questions very soon because, like, the results were coming in, nice results in circuit complexity, but then, you know, the progress, like, halted, and we haven't been making any significant progress since then. All right, so I'll see you guys tomorrow.